Yeah. So with that being said, let's get started. And so block multiplication, let A be a M by N matrix. Let A be a M by N matrix and B an N by R matrix. It's often useful to partition A and B and express the product in terms of submatrices A and B. Consider the following four matrices. Case 1. So we have four cases we have to consider. Four cases. If B is equal to B1, B2, so it's like you take the matrix B and you subdivide it into one block called B1, and then another block called B2. Now B1 is a n by t matrix. So this one here is a n by t matrix, and then B2 is a n by R minus T matrix. Then the product A times B, A being a M by N multiplied by B, will be equal to U factoring out. It's as if you were actually distributing A to the matrix B. That gives you A times B1 and then A times B2. Thus, A multiplied by the block B1, B2 will be equal to A times the block number 1 and then A times the block number 2 in the second big column. Now, case number 2. If A is equal to A1, 2, so you take A and you partition it in terms of row, you partition it by row so that you create two matrices. The first one called A sub 1 and the other one is called A sub 2, where K is a K by N matrix and A2 is a K by N matrix. So yes, and then no. So where A sub 1 is a K by N matrix and A2 is a M minus K by N matrix. So here is a typo. Here there's a typo. Okay. So the second case, A is a matrix with such that A sub 1 is a K by N matrix and A sub 2 is a M minus K time N matrix. Then we have the following. You can multiply if you want to do the product A and B. You break down A in terms of block matrix and multiply by B, and it's as if you were distributing B going in the first block and then B multiplied by the second block. So B is multiplied by the first block and B is multiplied by the second block. Now the third case. Let A be a so before I even continue, I want to say that in order for you to be able to multiply the blocks, let's do it here. You will see it here. So in order for us, so let A equals to the matrix A11 divided in two blocks, A1 and then A2. So A1 is a matrix, A2 is a matrix. Here you have a block partitioned by rows. So here it's partitioned by column, and here it's partitioned by rows. So B1 you have a vector B1 and then another vector, no, not vector, matrix B1 and another matrix B2, where A1 is a M by S matrix, A2 is a M by N minus S matrix, and then the matrix B1 that is over here is a S by R matrix, and B2 is a N minus R times R matrix. Now notice something. In order for you to be able to do the product A times B, the columns of this submatrix over here has to be equal to the number of rows of that submatrix over here. So here we have the matrix A sub 1. A sub 1 has N minus S columns. Let me see. A sub 1 has S column. A sub 1 here as S column. So this matrix over here as S column, and that should be equal to the number of rows of this submatrix over here. B sub 1 is a S by R matrix. So you can see that the number of columns of this one has to be equal to the number of rows of that one over here in order for you to be able to perform that that product. Uh, so let's continue. So case number 3, let A equals to this block over here, matrix A broken down into A sub 1 and A sub 2 blocks, and B equal to B1, B2 columns, B1, B2 matrices in terms of blocks. So then we have the following: if C equals to A times B, then we have C sub ij equals to the sum L goes from 1 to N of A sub I L multiplied by kind of like a product of B sub Lj. And that can be further broken down into a matrix. This is like a product of a matrix. Now this is like a matrix, and then this is another matrix. The product of two matrices here, and the product of another two matrices over here. So notice here it represents the number of columns. The n over here represents the number of columns. So we go from because we know that A is the m by n matrix. So we have n columns in total, and that those n columns are being subdivided into s columns, and so n, and then n minus s columns. So here normally you have like a s, and if you deduct s from n, you have n minus s. So we start here from 1 to s column. Here this matrix s a1 as s column, and this matrix here as n minus s column. So we go from 1 to s, and then we multiply that by the corresponding matrix B over here. So that's why we have this sum. The entry I, L, B, L, J, L going from 1 to S. So that means we are dealing with these two matrices, plus, so the plus in the middle, these A2 times B2, the scalar product of these two. So you have a matrix going from L goes from S plus 1, because here we had S column. So here we are starting at the S plus 1 column, and we go all the way to N. So L goes from S plus 1 all the way to N of A of this matrix over here, time this other matrix over here, B2. And B2, and these are represented this way. So we're doing the sum product of the IF entry and BJF entry over the columns. We are changing it over the columns. So this is the product over here. It's easier to see when it is an example rather than a formula. Thus, the Cij is the sum of the ij entry of the matrix A1, A sub 1 times B1, and the ij entry of the A2 sub B2. Therefore, A times B, which is equal to C, equals to A1 B1 plus A2 B2. So you take it as if it was a regular product of vectors. So you think about it as if it was a vector. So here think about it as if it was a row vector, and this one as if it was a column vector. You take this row, this element times this column, this element plus this element times this other element, and then you obtain the results. So it follows that A1 A2 equal time B1 B2 will be this product over here. So now there's another case, a fourth case. Let's assume now that A and B are partitioned as follows. So you have A being into like four different blocks and B being into four different blocks. Uh, so from here we have k rows and m minus k rows here. Here in the top we have k rows, and in terms of column we have s column, and here n minus s column. Now, for the BF matrix, so the second matrix, we have um, we have s rows and n minus and then so it's like you have a matrix over here. Now, for this matrix, you have s rows and then n minus s rows underneath. In terms of the columns, you have t columns, and the remaining columns have a dimension of r minus t columns. Now, let a sub 1, so we can break down the matrices as follows. Hold on 1 second. I think I'm being asked outside. Hold on 1 second. Okay, so it's like let's say you have a matrix A1. I'm back. So let's say you have a matrix A1. A1 is like your first block matrix with entries A sub 1 1, and another block matrix A sub 2 1, and the second block of the matrix is A2 with entries A sub 1 2, and the other entry A sub 2 2, and you have B sub 1 being that other matrix B1 broken down by columns, and and then you have B2 also broken down in terms of columns with these entries B sub 2 1 and B sub 2 2. So again, here when you have blocks like this, you have to actually when you have blocks of matrix, you have to think about it as if it was like regular matrices, no, like regular matrices where these are vectors and numbers. So think about it as if it was normal matrices. Don't think about it as if it was a block. So A times B equals to this matrix times this matrix, and you obtain this, just like as if it was a regular matrix. So therefore, you have this block of matrix times this other block of matrices will give you the following. So we can even try to do it on paper or quick. Let's try to do this one on paper. So you have You have a matrix like this one, A sub 1 1, A sub 1 2, A sub 2 1, A sub 2 2. You take it as if it was a regular matrix, regular product of matrix. Again, this is like a block, this is like a block of matrix. And that's gonna give you like, you take this block, this set of block, this set of blocks, this one, and you're gonna store it over here. So it's like you fix the column. So we're fixing this column over here, this time this, store it over here, this time this, and I store it over here. Then I move on to the next column, take this row times this column, this row times this column. A11, B11 plus A12, B21, and A21, B11 plus this times this, as if it was like a regular normal type of thing. A11, B12 plus A12 times B22, A21, B12 plus A22, B22. So you have one block multiplied by another block, and you have that matrix. So it's like a block like this one could have been something like this, like 1 1 2 1 2 2 4 4 1 1 2 3, and 4 3 1 2. You have something like that, and you break it down in block, and then you call this one A11, call this one A12, call this one A21, A22, something like that. So you can, like, in terms of blocks, like these blocks are actually matrices like this. B also will have the same structure as A. So let's go back to the notes. So in general, if the blocks have a proper dimensions, the block multiplication can be carried out in some manner, in the same manner as ordinary matrix multiplication. That is, if A equals to this matrix over here, and with blocks as entries, and B being another matrix with blocks as entries, then A times B will be a matrix with blocks as entries, where Cij is going to be equal to the scalar product of k goes from 1 to t of one block of the matrix multiplied by the other block of matrix. So the multiplication can be carried out in this manner only if the number of columns of AK, so the number of columns of this one, is equal to the number of rows of B sub Kj. So the multiplication can be carried out in this manner only if the number of columns of A sub Ik equals to the number of rows of B sub Kj for HK. So let A equal to this matrix and B equaling to this other matrix with blocks inside. Partition. So let A equaling this and B equaling that. Now partition A into 4 blocks and perform the block multiplication. So let's try to solve this one. We want to try to solve this one. We want to partition this matrix first. And once it is partitioned, and you want to partition so that we can do the multiplication of block. So let's try to do this one. So we start with the matrix A being equal to 1, 2, and then 3, 1, 2, 3 here, 1, 1, 2, 1, 1, 2, like this. And you have another matrix called B with the following entries. The following entries: 1, 1, 1, 2, and 1, 1, 1, 1, 3, 1, 3, 2, 1, 1, 1, 2. Partition this way. Okay. So since A, so we want to find we want to perform the block multiplication. So since each, so here's the formula: Cij has to be equal to the sum. K goes from 1 to T of I entry here, J entry here, K here, K here. Now, since in each B sub BKJ has two rows, so meaning that these matrices here, this is my B matrices. B K here is gonna be 1, 1. So here my BKJ, meaning this entry, this matrix has two rows, right? That means my I sub IKJ should have also two columns. I need to break down so that I have two columns. So since B sub KJ has two rows, the A sub IK, they must have two columns. So let's start with the first one. So in order for us, so there are two possibilities. So there are two possibilities for this situation. So we want to do what we want to do is to create a situation where we have let's do it so that you can see. So the first possibility will be us starting with this one over here: 1, 1, 2, 2, 3, 3, 1, 1, 1, 1, 2, and then 2. I have to I need to have two columns on my A matrices. So in other words, I should have something like that, two columns. Now these two columns will come at a cost. There will be two situations. Either I have this a block here, I have a block here, or I have another block here. So let me draw it. So either I have this block. Okay, so for these entry in two columns, or in a second place, I have this situation. So this is my A matrix. So A is going to be equal to this second matrix over here: 1, 1, 2, 3, 3, 1, 1, 1, 1, 2, 2. The columns are separated, but instead of being the block starting over here, I have a block over here. So we're going to start to do it case by case. So that's going to be our case number one. That's going to be our case number two. So case one, the first case, A times B will be equal to the matrix over here, 1, 1, 1, 1, and then 2, 2, 3, 3, 1, 1, 1, 2, 2. That's A, right? And the entries, actually, this here is actually our A sub 1, 1. This here is our A sub 2, row 1, column 2. And this one over here is our A21. This one over here is our A22, like this. So we have this matrix multiplied by this other matrix B, and B is the following: 1, 1, 1, 2, and 1, 1, 1, 1, 3, 1, 3, 2, 1, 1, 1, 2. So that's my matrix A multiplied by my matrix B. And as you know, the same entries like B, 1, 1 here, B, 1, 2, B, 2, 1, and here B, 2, 2. So if I do the product, this is what I get. I take this row here times this column over here as if it was a regular type of matrix. So 1, 1 here multiplied by this matrix over here, 1, 1, 2, 2, plus, so this time this plus this time that, 1, 1 time 3, 1, 3, 2, and then I continue. So it's like I fix this column over here, multiply this time this, finish that, now this time that. So this matrix over here, 2, 2, 3, 3, multiply by this time that, 1, 1, 1, 2,
Yes, sir.
plus this time this, 1, 1, 2, 2, time 3, 1, 3, 2. Okay, so that's like the first block that we finished. Now we're moving on. We did this time this, and then this time that. Now I'm moving now to the second column. So now everything that's going to be stored in this box. Now take this second column. This is the second column. So row here times column here, and then row here times column over here. So that's going to be 1, 1
Yes, sir.
time 1, 1, 1, 1
Sir.
plus 1, 1 time 1, 1, 1, 2. And here I have uh, so row time column. Now row time column. Here I have 2, 2, 3, 3 time 1, 1, 1, 1 plus 1, 1, 2, 2, and finally 1, 1, 1, 2. Okay. Now, if I do the product this time, this if I do the calculation in the end, this is what I get. A B equals to 8, 6, 4, 5, 10, 9, 6, 7, 18, 15, 10, and then 12. Now, because like this is our matrix A, and this is our matrix B. So the way we break down A, the value, the matrix in the left side, is the same way we're going to break down our result. Now let's move on to the next one. The way we break down, we created block with A, who's gonna be the same way we do it with B.
Sir,
Yes,
there is someone who is asking a question. We want to ask a question.
let's go ahead.
Sir, I think there's a problem with matrix B11 in the first line, because you wrote A11 time
So show me,
one, and it's supposed to be 1 2 instead of
so
2 2.
show me, point my finger here. You're talking about this matrix here, here. What's the position? What's the
Uh,
position?
the position is the first line you okay, the second line actually
Second
you
line.
roll one time. Yeah.
Here.
The position is the first column, first line,
First column,
first row,
first
first
row,
column.
and then first column. So here, right? You're talking about this section?
First one, first, yeah, first row, first column of
Okay.
the
So let,
multiplication.
so let me verify to see. Maybe you're right. I'm just copying from my
Actually,
notes. So maybe you're right.
I have internet, so I can really see.
I haven't heard what you said.
Sir, I think I get what he said. You put
Mm-hmm.
a two instead of one during your
Two instead of one here. Let me check. Let me double check.
the
So
first
we
one.
have this one times this one. Yes, I see. I see what you mean
Yeah,
here.
instead of 1 2.
Yeah, yeah. That's true. That's correct. That's correct. I didn't type it. Okay, yeah. That's correct. That's correct. So this one times this one plus this one times that one. So yeah, you're following. Thank you very much. That's correct. You're right.
You're welcome,
But
sir.
that doesn't change the final result. It's me when I was actually writing it here, I made a mistake. But like on the paper, the value is the same. But the final result should be this one in the end. Now the next one is so thank you for that. So now this was the first case. This was the first case. Now let's move on to the next case. The next case we have to break down the matrix in a different way. Case number two. So we have your matrix over here, A. So instead of breaking it down in this row, we're going to use that row over here, but we still keep the two columns. So one, one, two, two, three, three, one, 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 two, two. So we break it down like this and then this way. Then the matrix B, as we all know, is this one. One, 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 two, one, 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 three, one, three, two, one, 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 two. So if we were to do the multiplication, in the end we get the same result. And in the way the matrix on the left is broken down, the same way our results is going to be broken down also. Okay. So any questions related to this one? Okay.
Sir,
So yes.
so no matter how we partition the matrix, if you multiply them in the same order, they are going to give the same results.
Now the way
Is
you
that?
partition the number of column of this one
Yeah.
uh should be equal to like the number of rows The number of rows of the other one
Mm-hmm.
should be equal to the number of rows of this one.
So as long as this rule is satisfied, it will be equal.
Mm-hmm.
No problem. Thank you,
As
sir.
long as this row is satisfied, you'll be able to do the multiplication.
Okay.
But
Thank
in
you,
this
sir.
case, you have two cases. Okay.
So,
Yes.
please, what's the meaning of partitioning the final result?
What's the meaning of it?
Yes, because
Okay.
we are done. We get our result. What are we? Yes, we got what I want to say. So,
So the question is, why are we partitioning? If you remember the what we said about the left multiplication, we're saying that it affects, like when you do the left multiplication, it affects the rows. Similarly, when you create blocks and you do a left multiplication with that block, that same partitioning will be reflected also on your final matrix. Okay, if you remember when we had elementary operations like E2, for example, E1 to a matrix, that affected the rows of the matrix, affected the rows. When we did the left multiplication last time in last class. Also here, when you have a block and you do a left multiplication to another block, the final result will still, like the final result, in the final result, the effect of that left multiplication will also be reflected on your final result. Okay.
okay, so
Yep. So we've seen previously, we've seen the concept, like if you have a row vector x transpose multiplied by a column vector y, you obtain what we call the inner product. This is called the inner product, and that's going to give you this product over here, uh, x1, x2, all the way to xn, multiplied by the column y1, y2, all the way to yn, and then that's going to be equal to this time this plus this time that plus that plus this time that. In other words, x1 times y1 plus that plus xn times yn. So the result will be like a scalar. Will be a one by one matrix or a scalar. So there's another type of product. This is called the inner product, but there's another type of product called the outer product. The outer product. The outer product. So instead of transposing the first vector, we are actually transposing the second vector. So if you have, for example, x, which is a vector, a row vector, a column vector multiplied by another column vector, but you transpose it in terms of a row, then you have the following: x sub 1, x sub 2, all the way to x sub n, multiplied by the transpose of the vector y with entries y1, y2, all the way to yn is going to give you the following. You take this row, you multiply that by this column. So you fix this column first, multiply this row by this column, and you store it in that row. So that's going to be x1, y1. You take the second, you still fix that y1 over here, and then you multiply row 2 times this column over here. So x2, y1, all the way to this one, xn times this one, xn, y1. Now you move on to the next column. Move on to the next column. And the next column is the following. This row times this column over here, x1 times y2. This row times this column over here, x2 times y2, all the way to xn y2. So you do the same thing for the other entries, and in the end you have x1 yn all the way to xn yn. So that's the what we call, this type of product is what we refer to as the outer product. And the outer product will give you a matrix as a result, whereas the inner product is going to give you like a scalar typically as a result. Let's see an example of that, of application. So let's say that you have a vector x like this equals to 4, 1, and 3. Another vector y equaling to 3, 5, and 2. And you're asked to find the outer product x times y transpose. So we can write x times y transpose equals to 4, 1, and 3 times the transpose of this one, 3, 5, and 2. That's going to be equal to this times this times that, this times that. 4 times 3, 1 times 3, and 3 times 3. So I'm done with this column. I'm moving on to the next column now, and then I'm going to restore the result in that row. So 4 times 5, 4 times 5, and 1 times 5, and 3 times 5. Next, we're going to move on. We're done with this column. We're moving on to the next column. So now we are using this space that represents the next column, and we're going to do row times column. 4 times the column here. Now next this one times this one, 1 times 2, and finally this one times this one, 3 multiplied by 2. Now we're calculating the following result, the final result. So 4 times 3 is 12. 3 times 1 is 3. 3 times 3 is 9. And here 20, 5, and 15. Here 8, 2, and then 6. So the outer product of this is this matrix, this given matrix. Now let's see some more example of this. So that's the case where we have, for example, 1 by n. Here we have a 1 by n. We have 1 by n vectors. 1 by n vectors. That's what we had. Now let's see if we had a matrices. Let's suppose that we have So for example, you have X being a M by N matrix. And let's assume that you have another matrix Y being a K by N matrix. Now what you want to do, you can form a matrix product X, Y transpose. We can partition the column of X and Y into rows and then perform block multiplication. So we can transform like we can partition X into columns, X into columns, and Y into rows to form block multiplication. So partition, let me into columns. So here we're gonna do partition into block multiplication. We can do that. Let's try to see if we do that. What's gonna happen? So you have like X, and then you have Y transpose. You decided to turn X into uh, columns, right? So if you decide to do so, you'll have like X1, X2, dot dot dot, Xn. So you decide to divide the columns of X into partition. Now, if you also want to do the same thing for the matrix Y, you have Y transpose 1, Y transpose 2, dot dot dot, Y transpose. Uh, we had N here, so N. Now, okay, so here we had so that is N rows, but we have like this is K rows, N columns, but Y transpose is gonna be N rows and then K columns. So they do have the same. So here the rows is equal to the number of column of this one. So the product is doable. So I can do now this times this plus um, I can do this time this plus this time this multiplied by this time this multiplied by this one, etc. That's going to be equal to x1 y1 transpose plus y1 x2 y2 transpose plus dot 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 plus xn yn transpose. So we can try to see it in terms of an example. Let's see an example of that. So you are given a matrix X, three, two, and then one, and another matrix with entries 1, 4, and 2. You have that matrix Y equal to 1, 2, and 3, 2, 4, and 1. You want to do the outer expansion. You want to compute the outer expansion. So here we have our matrix X that can be broken down into a, we can call this we can break down our X matrix in columns over here. And here we have like X1, and here we'll have our X2, X2. Now the transpose of this one, so we need the transpose of this one. Y transpose will look like this. look like so the rows becomes columns and vice versa. So one, two, two, four, three, one. So here our y like our y1 transpose is this one, and our y2 transpose is this one. Okay. So now, as you can notice, the number of rows of this one is equal to the number of columns of the number of rows of one is equal to the number of columns of the other one. So let's try to do our product over here. So let me use even the formula. Formula says this: x1 times y1 transpose and plus x2 times y2 transpose. Here my x1 is this column over here, 3, 2, and 1, time y1 transpose is this one over here, um, 1, 2, 3, 1, 2, and then 3, plus x2, this column vector over here, 1, 4, and then 2, time y2 transpose is this one over here, 4, 2, 4, and then 1. Now, I can do now the product. I block this column and I do this row times this column and I store the result in the row. This row times this column, I store the result in a row. This row times this column and I store the result in a row. That's going to be, I store the column, block this column, 3 times 1 is just 3. 2 times 1 is just 2. 1 times 1 is just 1. Now moving on to the next column, 3 times 2 is just 6. 2 times 2 is just 4. And then 2 times 1 is just 2. Moving on here, 3 times 3, 9. And then 6. And then 3. Plus in the middle. Now moving on here, I do the same thing. I block this one, this time this time this time that. So I get 2, 8, and then 4. Moving on to the next, this time this time this time that. So 4, 16, and 8. And I block this one, this time that. So 1, 4, 2. Now I'm doing now the addition of matrices. I'm going to do now the addition of matrices. And for the addition of matrices, all I have to do is just to add the entries. This time this time this time that, etc. So 2 times 3 times 2, 5, 10, 10 here, 10, 20, and then 10, 5, 10, 5. So that's going to be 5, 10, 5, 10, 20, 10, 10, 10, 5. X, Y transpose. Okay. So any questions related to so here is when they ask you specifically to find the outer expansion. Find the outer expansion. The outer expansion of XY transpose. That's when they ask you that. And when they ask you that to do this type of product. So any questions related to this one? Okay, so we've done this block multiplication. I think we were doing this example. We set A, we had the matrix A, and we needed to multiply by matrix B, and we partition A, and we're able to do the multiplication. Let me go over these parts. So the outer product expansions. Given two vectors x and y in Rn, the product x transpose multiplied by y is a product of a row vector, a 1 by n matrix, and a column vector, a n by 1 matrix. The result will be a 1 by 1 matrix or simply a scalar. So x transpose time y is equal to this, and we get that in the end. This type of product is referred to as a scalar product or an inner product. The matrix product x times y transpose equals to the vector column vector x multiplied by the column vector y transpose. So we obtain a row vector, and that's going to give us a matrix. So the product x times y transpose, as you can see, the transpose is outside, is referred to as the outer product of x and y. For inner product, the transpose is inside like this, and the outer product, the transpose is outside. So x times y transpose is referred to as the outer product of x and y. Now I think we've already done this example in the notes. This is what I've done like a few seconds ago. So suppose that we start with a M by N matrix X and a K by N matrix Y. We can then form a matrix product X times Y transpose. If we partition X into columns and Y into rows and perform the block multiplication, we see that X times Y transpose can be represented as a sum of outer product of vectors. So you have this times this equal to this one and that one, and we have the sum of the outer product of vectors. So this representation is referred to as an outer product expansion. And the example that we've just done was this example, x and y. You want to find the outer product expansion. And that's what we've done. Now, with that being said, exercises from 1 to 22 of the book, page 94 to 96. Normally, if you do like 4 problems per day, by next week you should be able to finish it. So any questions related to this? So let's move on to the next one. Okay, it's coming. So determinant. So that's the next topic that we're going to be discussing. The determinant of a matrix. So with each n by n matrix A, it is possible to associate a scalar, and that scalar is called the determinant, whose value will tell us whether the matrix is non-singular. So the determinant is a value that allows us. It's a value that has a function, and that function allows us to know whether or not a matrix is non-singular. So let's observe different cases before we can generalize. So case number 1, you have a 1 by 1 matrix. Now you have a 1 by 1 matrix, it's actually a number. So case 1 by 1 matrices. If A is equal to just the entry A is a 1 by 1 matrix, then A will have a multiplicative inverse if and only if A is not equal to 0. And thus we define the determinant determinant of the matrix A being the value A. Then A will be non-singular if and only if that determinant of A is non-zero. Now let's look at the second case. Okay. Still on the first case. So if we look at the first case, you have a matrix A, which is a one by one matrix. Now, this is like our regular type of uh, values. If like in order for this matrix to be invertible, meaning that if you want to find the inverse of this one, here we are in a one-dimensional space. Very now, if you want to like think about the inverse of a matrix as the fact that we can have like 1 over something. But since it's a matrix, you cannot talk about 1 over that. But in order for this matrix A to be invertible, this one has to exist, 1 over A, so that if I multiply them together, I get 1. So like the multiplicative inverse of that matrix A is just 1 over A. Now, in order for that 1 over A to exist, that value over here should not be equal to 0. Okay? Now, if you wanted to generalize this, we can say that in order for this matrix A to not be equal, to be invertible, there need to exist another matrix, another value, a value over here called the determinant of A, such that that determinant of A is not equal to 0. Okay. So originally we have a matrix A. In order for that matrix A to exist, to be invertible, there need to exist a value, another value, and such that that value is not equal to 0. Because if it's equal to 0, it doesn't exist. This expression does not exist. And that value that needs to exist is what we call the determinant. So for a matrix to be non-singular, there need to exist a value called the determinant, and that determinant should not be equal to 0. So this is where we're going to stop. We're going to continue. For those who are going to be here on Friday, we're going to continue on Friday. If you cannot attend, it's not a problem. It's not a problem. Just watch the video of the class, and yeah, we watch the video of the class. And if you have questions, you can ask later on. So yes, let me take. I will take attendance, and we're going to, and we'll stop. So any questions related to this?
Yes, sir. I
There's a
have a question, but not
uh,
related to this.
I hear two voices at the same time. I don't know who is talking, who is not talking, and I don't hear the question. So what was the question?
So I have a
Yes,
question, but related to the course, not to this lesson, sir.
related to
If
the class.
yes, sir. So
You said to
why
the related to the.
to the class in
Mhm.
general? Why do we have so much reading assignments, sir?
Oh no, I don't know if you've read correctly the email related to the reading assignment.
I
You
write.
have the reading is you have five you have 5 subjects. You have 5 articles. Out of those 5 articles, you select 3 to do the summary of those 3.
Eh, that's what I said, sir.
It's not like
Even
you read all
three
of them.
is too much, sir. We are in math
No,
class,
3 is
sir.
a good
You are
number.
making us read. Eh,
Yeah, you do your
I know that these reading assignment are replacing the quizzes
best.
that we were supposed
It's
to.
not like
Hmm?
you said. Okay, I haven't heard what you said.
I said that
I haven't heard what you said.
I said that the reading assignment that you gave us, I know that they are replacing the quizzes that we were supposed to do. So or not?
It's like I think it's like a compensation for the quiz or
That's
something like that.
that's what I'm saying.
That's what.
But
Yes.
sir, I
Yes.
have a problem. Whenever I have in front of me a text,
Mm-hmm.
we contain more than 500 words. My head is that. So is a real problem, health
But
problem.
she trusts the process.
But
Since
like
I'm
after
little, sir.
he said, I haven't heard you.
Since I'm a little kid, I have this problem with the text. Sir. It's not very easy.
But after like you will be asked, I think by the time you graduate, and also another like the usefulness of this is that before you graduate, they'll ask you to write a thesis, and it's a very long article. And most of the time, what happens is that students don't even know where to start. So if you have the habit of reading these kind of tests, trying to write your own thesis will be easy because you already have information on different topics. So that's why I feel like it's important for you now to start being initiated to that, so that by the time you reach graduation time, you already seen articles, what they look like. You can have some kind of inspiration to start to write your own thesis. So that's why I feel like it's useful. So,
Okay, sir.
yeah, so it's for your own good.
Yes, but she trusts the
Yes.
process.
So okay, so let me read the attendance. Aka Cyril told me that he has internet
Yes, sir.
connection.
I'm present. I'm present.
All right.
Elected member.
Ako
Present, sir.
in Aleppo, Linda.
Present, sir.
All right. Kulibali, in Ile,
Present, sir.
Present,
Fofana,
sir.
Fofana, and Hassan.
I'm here, sir.
All right. Lai, Merlik,
Present, sir.
Ouattara Idriss,
Present, sir.
Idriss,
Present, sir.
Star.
Present, sir.
All right. Toreno, Toreno, Toreno,
Present, sir.
Touré Sheikh,
Present, sir.
and Touré Malaika. Touré Malaika.
Present, sir.
All right. So with that being said, I'll see you probably on Friday. All right. So take good care of yourself, and I'll see you.